To enhance the reliability and effectiveness of emergency lighting systems, consider revising the building code to require the monitoring of all electrical phases within a room that contains multiple lighting circuits. This will ensure emergency lighting is activated whenever any of the circuits feeding the room experiences a power failure. Monitoring all phases ensures that emergency lighting will activate regardless of which circuit is tripped. This is crucial in situations where engineers may have designed a room with more lights than necessary, leading to the possibility of only half the lights being used during normal operation. By requiring the monitoring of all phases, the code would promote the responsible use of energy. Engineers would be incentivized to design lighting systems that only illuminate the necessary areas, reducing overall energy consumption. In the event of a power outage, it is essential for emergency lighting to be available throughout the room to facilitate safe evacuation and operations. Monitoring all phases ensures that emergency lighting is available even if only a portion of the room has electrical power. To implement this change, the built-in code could be amended to include the following requirement. In rooms containing multiple lighting circuits, emergency lighting load shall be connected to a monitoring system that detects power interruptions on any of the circuits feeding the room. Upon detection of a power interruption, the emergency lighting load shall activate. The monitoring system should be designed to be sensitive enough to detect power interruptions on all phases. The monitoring system should be located in a secure area to prevent tampering or damage. Regular testing and maintenance of the monitoring system is necessary to ensure its proper operation. By requiring the monitoring of all electrical phases within a room containing multiple lighting circuits, the building code can be improved to enhance the reliability, energy efficiency, and emergency response effectiveness of electrical systems. This change would benefit building occupants and first responders alike. Considering this proposed change, the current approach often relies on a single circuit to power emergency lighting or, in larger installations, selecting one circuit out of a few to tie the emergency lighting to. However, this method has potential drawbacks, particularly in modern energy-efficient designs where lighting circuits might be underutilized during normal operation. Monitoring all electrical phases addresses these issues by ensuring that emergency lighting activates whenever any circuit in the room fails. This is especially relevant given the increasing emphasis on energy conservation, leading to lighting designs that may not fully utilize all available circuits. The increased reliability stems from the comprehensive monitoring of all phases. Instead of relying on a single circuit, the system detects power interruptions on any circuit feeding the room. This is crucial because if only a fraction of the lights are in use, a failure in an unutilized circuit would go unnoticed until an actual emergency. By monitoring all phases, the system ensures that emergency lighting is activated regardless of which circuit trips. Energy efficiency is also enhanced. By requiring the monitoring of all phases, engineers are incentivized to design lighting systems that only illuminate the necessary areas. This promotes responsible energy use, as there is no advantage to installing excess lighting that may not be used. Improved emergency response is a direct result of the enhanced reliability. In a power outage, complete and immediate illumination is critical for safe evacuation and operations. Monitoring all phases guarantees that emergency lighting is available even if only a portion of the room is powered, ensuring that occupants and first responders have adequate visibility. Implementation requires amending the building code to include a specific requirement for monitoring systems in rooms with multiple lighting circuits. This requirement would mandate that emergency lighting loads be connected to a system that detects power interruptions on any of the circuits feeding the room. Upon detecting an interruption, the emergency lighting load must immediately activate. Furthermore, there are some additional considerations. Firstly, the monitoring system needs to be sensitive enough to detect power interruptions on all phases. This requires a robust design that can accurately identify even brief or partial power losses. Secondly, the monitoring system should be located in a secure area to prevent tampering or damage. This ensures that the system remains operational and reliable when needed. Thirdly, regular testing and maintenance are essential to ensure the proper operation of the monitoring system. This includes periodic checks of the sensors, wiring, and activation mechanisms to identify and address any potential issues. The benefits of implementing this change are significant. It improves the reliability of emergency lighting, enhances energy efficiency, and promotes a safer environment for building occupants and first responders. By requiring the monitoring of all electrical phases, the building code can be updated to reflect modern lighting design practices and improve overall safety. To further elaborate on the technical aspects, consider the design of the monitoring system itself. It could be implemented using current sensors, voltage sensors, or a combination of both. Current sensors would detect the flow of current in each phase, while voltage sensors would monitor the voltage levels. If the current or voltage falls below a certain threshold, the system would trigger the emergency lighting. The specific type of sensor used would depend on the characteristics of the electrical system and the desired level of sensitivity. In addition to the sensors, the monitoring system would also need a control unit to process the sensor data and activate the emergency lighting. This control unit could be a programmable logic controller, a microcontroller, or a dedicated circuit. The control unit would need to be programmed to recognize power interruptions and to activate the emergency lighting accordingly. The emergency lighting itself could be powered by a battery backup system, a generator, or a separate emergency power supply. The choice of power source would depend on the size of the building, the criticality of the lighting, and the budget. The emergency lighting should also meet the requirements of the National Electrical Code, NEC, and other applicable standards. The NEC provides specific guidance on the design, installation, and maintenance of emergency lighting systems. The NEC Article 700 covers emergency systems in general, including the requirements for power sources, wiring, and control devices. The NEC Article 701 covers legally required standby systems which are similar to emergency systems but are not required by law. The NEC Article 702 covers optional standby systems which are used to provide power to critical loads during power outages. The NEC 310.15 provides tables for determining the ampacity of conductors based on their size, insulation type, and ambient temperature. The NEC Table 310.15b16 is commonly used to determine the ampacity of conductors in raceways or cables. When designing an emergency lighting system, it is important to consider the voltage drop in the wiring. Voltage drop can reduce the brightness of the lights and can even cause them to fail. The NEC provides guidance on voltage drop in Article 210.19 AON for branch circuits and 215.2 AON for feeders. The NEC recommends limiting the voltage drop to 3% for lighting circuits and 5% for power circuits. To minimize voltage drop, it is important to use the correct size conductors and to keep the wiring runs as short as possible. In addition to the technical aspects, it is also important to consider the human factors when designing an emergency lighting system. The light should be bright enough to provide adequate visibility, but not so bright that they cause glare. The light should also be located in strategic locations to illuminate pathways and exits. The lighting should be designed to provide a uniform level of illumination throughout the room. The color temperature of the light should also be considered. Cooler color temperatures, such as those in the range of 5000 Kelvin to 6500 Kelvin, are generally more effective at providing alertness and visibility. Warmer color temperatures, such as those in the range of 2700 Kelvin to 3000 Kelvin, are more relaxing and comfortable. The choice of color temperature should depend on the intended use of the lighting. The monitoring system should also be designed to be user-friendly and easy to understand. The system should provide clear indications of any power interruptions and should allow for easy testing and maintenance. The system should also be designed to prevent false alarms. The monitoring system could be integrated with the Building Automation System (BAS). This would allow the BAS to monitor the status of the emergency lighting system and to provide alerts if there are any problems. The BAS could also be used to control the emergency lighting system, such as by turning the lights on or off or by adjusting the brightness. The monitoring system can also be designed to communicate with a central monitoring station. This would allow the monitoring station to monitor the status of the emergency lighting system and to dispatch emergency personnel if there are any problems. The central monitoring station could also provide remote testing and maintenance of the system. When selecting a monitoring system, it is important to consider the following factors. Firstly, the sensitivity of the system. Secondly, the reliability of the system. Thirdly, the ease of use of the system. Fourthly, the cost of the system. And fifthly, the maintenance requirements of the system. The monitoring system should be able to detect power interruptions on all phases. The system should be reliable and should not generate false alarms. The system should be easy to use and should provide clear indications of any problems. The system should be cost-effective and should not require excessive maintenance. The implementation of this proposed change will require coordination between electrical engineers, building inspectors, and building owners. Electrical engineers will need to design the monitoring system and to ensure that it meets the requirements of the building code and the NEC. Building inspectors will need to inspect the installation of the monitoring system and to verify that it is functioning properly. Building owners will need to provide access to the electrical system and to ensure that the monitoring system is properly maintained. The benefits of implementing this change will outweigh the costs. The change will improve the reliability of emergency lighting, enhance energy efficiency, and promote a safer environment for building occupants and first responders. The change will also help to reduce the risk of accidents and injuries during power outages. The proposed change to the building code is a valuable improvement that will enhance the safety and reliability of emergency lighting systems. It is a necessary step to ensure that buildings are equipped to handle power outages effectively and to protect the occupants and first responders who rely on emergency lighting in critical situations. By taking a comprehensive approach to monitoring all electrical phases, the building code can promote safer and more energy-efficient buildings. In terms of specific components for the monitoring system, consider these aspects. Current transformers, CTs, are often used to measure the current in each phase. They provide a safe and isolated way to monitor the current without directly connecting to the high-voltage conductors. The CT output a low current signal that is proportional to the current in the conductor, which can then be easily measured by the control unit. Voltage transformers, VTs, also known as potential transformers, PTs, are used to measure the voltage in each phase. Similar to CT, they provide a safe and isolated way to monitor the voltage. They output a low voltage signal that is proportional to the voltage in the conductor, which can then be easily measured by the control unit. Surge protection devices, SPDs, are essential for protecting the monitoring system from voltage surges caused by lightning or other electrical disturbances. SPD should be installed on all input and output circuits of the monitoring system. A programmable logic controller, PLC, is a common choice for the control unit. PLC are robust and reliable industrial controllers that can be programmed to perform a wide variety of tasks. They can easily interface with CT, VTs, and other sensors, and they can be programmed to activate the emergency lighting based on the sensor data. A human-machine interface, HMI, is a display that allows users to monitor the status of the monitoring system and to make adjustments to the settings. The HMI can be a simple text display or a more sophisticated graphical display. The HMI should provide clear and concise information about the status of the system, such as the current and voltage in each phase, and the status of the emergency lighting. Uninterruptible power supplies, UPSs, provide backup power to the monitoring system in the event of a power outage. The UPS ensures that the monitoring system continues to function even when the main power supply is interrupted. The UPS should be sized to provide enough power to the monitoring system for at least 15 minutes as required by the NEC 700.12. Proper grounding is essential for the safety and reliability of the monitoring system. The system should be grounded in accordance with the NEC 250. All metal enclosures and components should be bonded together and connected to a common grounding electrode. The ground fault circuit interrupters, GFCIs, provide protection against electrical shock. GFCIs should be installed in all wet locations, such as bathrooms and kitchens, and in any location where there is a risk of electric shock. Arc fault circuit interrupters of size provide protection against fires caused by electrical arcs. A size should be installed in all branch circuits that supply power to lighting outlets and other electrical devices. Regular inspections and testing are essential for maintaining the safety and reliability of the monitoring system. The system should be inspected and tested at least annually by a qualified electrician. The inspection should include a visual check of all components, a functional test of the emergency lighting, and a test of the grounding system. All test results should be documented and kept on file. Consider the following scenario when designing the monitoring system. A large office building has multiple lighting circuits in each room. The building owner wants to improve the reliability of the emergency lighting system and to ensure that the lights are activated whenever there is a power outage. The electrical engineer designs a monitoring system that uses current transformers, CTs, to monitor a current in each phase of the lighting circuits. The CT are connected to a programmable logic controller, PLC, which is programmed to activate the emergency lighting if the current in any phase falls below a certain threshold. The PLC is also connected to a human-machine interface, HMI, which allows the building owner to monitor the status of the system. The system is powered by an uninterruptible power supply, UPS, which provides backup power in the event of a power outage. The system is grounded in accordance with the NEC 250. The system is inspected and tested annually by a qualified electrician. This proposed system would provide a high level of reliability and would ensure that the emergency lighting is activated whenever there is a power outage. It would also provide the building owner with valuable information about the status of the electrical system. In conclusion, the proposed change to the building code to require monitoring of all electrical phases within a room containing multiple lighting circuits is a valuable improvement that will enhance the reliability, energy efficiency, and emergency response effectiveness of electrical systems. This change would benefit building occupants and first responders alike, and it is a necessary step to ensure that buildings are equipped to handle power outages safely and effectively. Remember that local codes and regulations might have additional requirements beyond the NEC, so always consult with local authorities having jurisdiction, OJ, for specific requirements in your area.